SOFIA itself is just like any other 747. It's a very nice airplane. It's a pleasure to fly. The hardest part about flying it is getting your body clock in tune with flying all night. The stars dictate how we fly.
Tower, NASA 747 Heavy, ready for takeoff, 25.
NASA 747 Heavy, hold short runway 25, await 95 release.
Hold short, 25, NASA 747 Heavy.
SOFIA stands for Stratospheric Observatory for Infrared Astronomy. It's a flying observatory. We don't know of any other observatory like this that's flying in the world.
NASA 747 Heavy, clear for takeoff.
Clear for takeoff.
It's an interesting blending of aeronautics and astronomical science. Part of the requirements for the design were that the airplane fly just like it did originally. The telescope itself is mounted in what would be the very aft portion of the cabin of the 747. And then there's a hole cut in the back of the airplane that allows the telescope to look out into the atmosphere.
The primary purpose for putting a telescope in an airplane is to fly high enough that the atmosphere is cold and the water vapor has all frozen out. Astronomers think water vapor is the problem. It blocks out light that you would otherwise want to be able to see. Flying at an altitude of, say, 43,000 feet, the amount of water vapor that's left above us is less than 0.5% of what you'd see down on the ground.
We just reached 40,000 feet.
Okay, thanks.
The main goals of SOFIA are to study the environment where stars are forming and what is happening there, and also how planets form, and then trying to put this into the bigger picture of how did life form. To answer these questions, we work with a variety of instruments. We use imagers, and we also have spectrometers that divide the light up, and that allows us to see the details of what material is there, the molecules and the elements that are out in space.
Still tuning? Yes.
The great instrument works like a classical radio. We can tune the receiver to the emission of far infrared wavelengths. And that is the typical radiation that we also experience when you get to a heater. That's why we call it the heat radiation or the far infrared radiation. Most of the interstellar medium, the gas, the dust that is between the stars, is radiating in the far infrared. And this is a material that we study because that's sort of the source for the next generation of stars to form. All the important ingredients that we need for life are made in stellar processing. Every piece of atom in our bodies has been cycled several times in stars, and that's always sort of exciting.
Center, good evening. Delta 1684 is passing 31.3 for 300.
How's the positioning, Ted? It's a little bit...
That looks fine, Alan. We're
a little high, that's all.
Yeah, when we've been 3 by 3 like this,
A little left, yeah.
we can take full frames at this rate.
The instrument that we built for SOFIA is called the High-Speed Imaging Photometer for Occultation.
Okay, Alan, and tell me when you're ready for the turn, please.
Turning now.
Any object you want to look at always has to be to your left. So you fly until you're done with that object, and then you make a turn to your next object and do another curvy loop. And before you know it, you've flown 10 hours and observed 8 to 15 different objects. It does get to be quite intense.
The final is 232 kilometers north of the reference position and 40 seconds early.
Okay.
And after this, it starts blending with another star, so they won't be getting any, well, they'll get more data, but it won't be of any good quality.
Yeah, right. Okay.
So I think we're done.
Let's just do it.
That's all we got.
Let's just do it.
Okay.
The main purpose in observing occultations is to work out the density of the atmosphere of the planet.
Okay, looks like the URG is now open.
Correct.
An occultation happens when a planet in our solar system happens to pass in front of a star. You can also think of it as the star casting a very faint shadow of the planet out into space. The starlight is refracted by the atmosphere of the planet. The atmosphere is acting a little bit like a lens. So our goal is to be at the right place at the right time so that the shadow goes over us. And obviously with an airplane, you have a real leg up. It's never cloudy, and you can be anywhere you want to be. Since Pluto's atmosphere was discovered in 1988 using this method, there have been several ground-based occultations observed. And it appears that Pluto's atmosphere is getting more dense, and we don't completely understand why.
This is the target star. That's Pluto. Pluto's moving this way. Just watch it move.
We're crossing the center line about now.
In the old days, our task was just to get somewhere in the shadow. The shadow is about as big as Australia.
It's getting weaker.
Yes.
Excellent.
But we've kind of upped the ante here. We're trying to get to the center of the shadow now. The center is diagnostic of the overall global structure of the atmosphere. It's a difficult measurement to make, but I'm hopeful that we'll be able to measure it with SOFIA.
Are the files saved?
Yeah, they're there. We're done.
Flying on SOFIA is a wonderful experience. When you open the door and start making observations that you cannot do any other way, and you see the data that no one has ever seen in the detail that you're looking at, it becomes very exciting.
There are high points and low points in every part of the operation. There are times when things don't work and you're completely frustrated, but then there are times when you finally figure out how to make it work. And generally speaking, on SOFIA, things do work.